Okay, welcome to the penultimate project, Project 4 for ME773. Again, I'm Jack Foxbeer. Let's get started. All right, for part 0, getting to know your classmate Jack a little bit further. I've been learning Japanese for 1.5 years. Is a little fun fact about me. I think Japanese is interesting and I think their culture is cool. So I thought, what better way to get to know it better is to learn the language. I think there are some funny words in Japanese. Here is an example. Initially, when I was learning this, it was very funny to me because it almost sounded like if you were maybe a racist person, how you would uh, make up and make fun of a Japanese person by uh, saying the word. So, for example, this word right here is basketball. They inherited it as a loan word. So they don't have their own word for basketball. They just took basketball, but it's pronounced in Japanese basketball. And I think that's so funny. So anyway, moving on. Uh, for this project, we were tasked to read the review paper by Bono et al., where this goes over everything about film-wise condensation, and particularly for this project outlines uh, Nusselt's original derivation of an average heat transfer coefficient for uh, horizontal pipes. So some of the assumptions uh, in Nusselt's derivation that they again outline, uh, we'll be considering the surrounding vapor at rest, saturated vapor, the wall temperature will be uniform, the condensate flow will be laminar and orthoradial. Uh, in the condensate film, there will be no shear stress at the liquid vapor interface. For heat transfer, we'll only be considering conduction, and then the condensate properties will be taken at the saturation temperature. So beginning with this derivation, we start with the momentum equation. We'll be considering the 2D momentum equation, stationary, orthogonal flow, and a cylinder film. So starting out, this is where we get our equation of momentum. For this first Nusselt's derivation, we'll neglect the pressure gradient. Some of the boundary conditions will be the no-slip condition. So the velocity at r equals 0 will be 0. And then the next boundary condition will be du dr at the film thickness will be 0. So no shear stress at the liquid vapor interface. This gives us an equation of our velocity, and then taking the average over the film thickness, we can get this over here, the U bar. Now from here, we need to take a mass balance on a portion of our condensate film, which can be seen here in this graphic. So this would be the tube wall, and then the condensate surrounding it. You have the mass flow in and the mass flow out, and the mass flux pushing inwards. So looking at this, where J sub theta is the mass flux, subbing in some of these equations that we've looked at into our previous equations, we can get our film thickness. So this is our film thickness here. And then again, considering heat transfer only transferred by pure conduction, H is lambda over the film thickness. We can get our average heat transfer coefficient by averaging it over the tube, which gives us here, which is our final answer and the correlation that we'll be using for these average heat transfer coefficients. There's some discrepancy among this initial constant here. Some have listed it as 0.725, and this is because I think, as the Bono et al. Paper said, initially Nusselt did a handmade Riemann sum or something like that. So there is a little bit of discrepancy, but for our purposes, this is not really matter. So for part 2A, we want to determine these average heat transfer coefficients for 3 refrigerants, so R134A and 2 of its global warming reducing potential refrigerants. So we'll utilize EASE to do this. EASE has the refrigerant fluid properties baked into it, so we don't have to use any separate tables or books to look up these refrigerant properties. We'll be considering a 5/8 inch horizontal tube a singular horizontal tube, and then a saturation temperature of 40 degrees Celsius. Then what will be varying is the fluid to wall temperature difference, and we'll be varying this from 3 to 10 degrees Celsius. Taking all that into account and putting it into ease, this is the initial results we get. So heat transfer coefficient on the y, the delta T on the x, R134A, it has the highest heat transfer coefficient, followed by 450A, then R513A. They all follow the same similar trend, starting out higher at around 430 watt per meter squared Kelvin, and then slowly decreasing as you increase the temperature. For part B, we want to look at for temperature differences of 3 and 10 degrees Celsius. We want to estimate the local condensate film thickness at 90 degree and 180 degree. So here is the equation to estimate the local condensate film thickness. It's one of the preliminary equations that was used to get the average heat transfer coefficient in Nusselt's derivation. So with this in mind, we could use ease once more, and then I used an integral calculator for the integral 0 to theta sine omega to the third. It was a little bit nasty of an integral. I tried to do it by hand at first, but I couldn't. It ended up using a sum. The integral calculator couldn't solve it, so it estimated it with a sum, but I think that is totally fine. So here's the results from doing that. As you can see, the film thickness at 180 degrees is thicker compared to on the top at 90 degrees, which is suggesting this is kind of looking at the influence of gravity. And all of the film thicknesses are pretty consistent for all of the refrigerants, R134A, then R1450A in the middle, and R513A on the far right. Dip and I actually had some conversations about this. We were like, well, we're a little bit concerned because our previous results, we were thinking R134A should have the highest or the lowest. R134A should have the lowest film thickness because it had that highest heat transfer coefficient, but it's actually the middle result. And this kind of shows that the heat transfer coefficient, while depending on this film thickness, is for these refrigerants being more impacted by the refrigerant properties itself, like viscosity and the thermal conductivity of it. Slide. So then for part 3, we were asked to use an alternative prediction for the average heat transfer coefficient H bar. This is actually the next equation in the Bono paper. It didn't have a source that I found, but it gives it in terms of a Nusselt number, which we can just solve for the heat transfer coefficient. H being the thermal conductivity, the length over, is that right? Nusselt being H, the length over the thermal conductivity. My bad. The differences between this correlation or this equation and the previous one, original Nusselt, this one takes into account the pressure gradient, where previously we did not, and this simplified the momentum equation. So now taking into account this pressure gradient, it will change the momentum equation. So solve this for H, and again, utilize ease. So this is the results to the right. You may have thought, oh, I thought this was the same graph as before, but no, it's different. The only difference is slightly lower heat transfer coefficients. So it's still pretty accurate, and there's a level of consistency with these results. So then for part 4, we're supposed to look at inundation. So inundation refers to the flooding or submerging of the tubes within the condenser. This is primarily due to gravitational effects. So with inundation, there will be the accumulation of water within the condenser. Again, inundation is going to happen when there's more than one tube as well. So as you can see, there's more than one tube in this figure. So water accumulates, and this will increase the surrounding condensate film. This increased thicker condensate film will then result in a higher or increased thermal resistance. Also, a higher subcooling of the condensate. With these both in mind, this should result in the next part in a lower heat transfer coefficient because of this increased thermal resistance. So as you can see, as you go down, the film thickness will get thicker as the water accumulates. So now we want to modify Nusselt's original equation to account for this. inundation effects. So we'll be considering the same refrigerant conditions for a delta T of 3 degrees Celsius in particular this time. We'll be looking at 6 inline vertical tubes, and they'll be isothermal. So kind of the case of A here. There's another equation in the Bono paper, the average heat transfer coefficient for an in amount of tubes by Jacob, 1949, where it's listed here. I think you could actually sub out this gamma term for a lowercase gamma, I think it was, and then this equation would kind of relate the heat transfer coefficient to a Reynolds number, which is kind of interesting. But here is where gamma is defined. So plugging this into E's, which solves for H, we can get the heat transfer coefficient for these 6 tubes with inundation effects accounted for. This is for the R134A case as well, in particular. All of the cases would have the same similar trends. So as originally in that first plot I showed, at a delta T of 3 degrees Celsius, R134 had a heat transfer coefficient of 427 watt per meter squared Kelvin. Now, when we consider 6 tubes and inundation effects of the water accumulating, we get a much lower heat transfer coefficient of 273, which, as we looked at earlier, makes sense. Some ways to kind of decrease the effects of inundation is to change the pattern of the tubes in the condenser. So here's an example of a more triangular pattern where they are offset instead of the straight down inline form. And then also you could look at the inline form, except while increasing the flow rate, which instead of a laminar flow, it would be some turbulent. You can see kind of splattering because of that. So here's some of the references, and that's the end. So thank you for listening. Get ready for the much asked for final project coming soon. So thank you again for listening. That is it.